Welcome to everyone. I am Daniele Calisi and I work for Magazino. I am going to talk about the use cases that we have been developing for the AI Plan for You project. The logistics automation use cases have been developed for AI Plan for You by Magazino together with the Örebro University. Magazino, a Hungarian company, is a leading robotics company specializing in the development and deployment of innovative warehouse automation solutions. Magazino's mission is to combine cutting-edge technology and artificial intelligence to enhance the efficiency, accuracy, and productivity of warehouse and the intralogistics processes. The company has two flagship products. Both of them are designed to work alongside human workers in dynamic environments. In particular, the Toru robot, on the left picture in this slide, is designed to independently store and retrieve shoe boxes and other small cartons in shelving racks. The Soto robot, on the right side, is designed for more industrial production environments, for example, those related to automotive manufacturing, bringing materials directly to the assembly line or to target compartments. For the AI Plan for You project, we worked together with Örebro University to actually provide two use cases. One is related to the on-offline tool to help the behavior designer, while the other allows for the use of planning technologies at runtime to compose basic activities in order to obtain complex behaviors. In Magazino, we use behavior trees to define the high-level behavior of our robots. Behavior trees are a well-known formalism that offers a visual representation of the decision-making processes that define robot behavior. This technology has multiple applications, also beyond robotics. In the behavior trees context, the execution and evaluation of the nodes is called ticking. The ticking process typically starts from the root node and moves through the tree, evaluating each node based on predefined policies, conditions, and priorities. In the picture on the right, we are showing a possible sequence of execution of the nodes in one tick of the behavior tree. The numbers show the sequence in which the nodes are traversed during this tick. Some runtime conditions are checked by the composite nodes, and depending on their result, some of their children can be processed or not. Some sequences of execution can then lead to violate some semantics constraint. For example, if we have a typical producer-consumer relationship between two nodes, it is possible that some runtime conditions prevent the producer to be executed before the consumer. In order to help the behavior designer to avoid this kind of mistakes, we decided to take advantage of the automated planning technologies in the following way. We defined the planning problem by including the structure of the tree to be analyzed, the current state of the nodes, and the rules to tick a node or advance to the next one. We defined the goal of the planning problem as to find a possible execution that violates some important constraint. For example, the producer-consumer relationship. In this way, if the planner is able to find a plan to this goal, it is providing us with a possible execution that violates the constraint and does need to be considered by the behavior designer in order to address this inconsistency and thus to improve the robustness of the behavior tree. With this formalization, the problem is a classical planning problem that can be defined using the universal planning library and solved by, for example, fast downward. We integrated this solution in our system as a Python script that is able to read one of the behavior trees that we have and convert it into a planning problem as I described in the previous slide, and then run a planner through the universal planning library. As I said before, this planner searches for possible executions that violates a producer-consumer constraint. In the future, more types of constraint checks can be implemented using the same technology. We constructed a set of behavior trees in order to evaluate the correctness of the method and also provided a Jupyter notebook to show the results. Two examples of behavior trees are shown in this slide. In the first case, the behavior tree is correct. In the behavior tree on the right, there is at least one possible execution that leads to the violation of the producer-consumer constraint. You can see the output of the script in the lower part of the picture. We used this technology to check a subset of our behavior trees. Other trees could not be analyzed yet because they contain nodes whose behavior are not defined yet in terms of the formalization given previously. Now I'm going to explain how we use the automated planning technologies for a second use case, that is at runtime, to dynamically decide the behavior of the robots. Our behavior trees are manually crafted by behavior designers. In some cases, this process is difficult, as many often conflicting conditions should be taken into account, especially when dealing with parallel activities, failures, recoveries, or in general, unexpected changes in the state. In order to model the problem, we took the following decisions. We took one of our behavior trees and we split it into a set of different activities, each of which is defined by a specific behavior tree. And the actions for the planning problem are defined as the possibility to start, abort, finish each of these activities. These activities then follow a simple state machine, as the one that is depicted in this slide. This allows the executor, afterwards, to decide whether to start, stop, or keep ticking the related behavior tree. The planning state is defined by a set of variables, most of which are kept up to date by reading it from sensor data. A goal is given at runtime, given some priorities, and taking into account the condition and situation. The introduction of the concept of optimality allowed the system to quickly respond to unexpected changes in the planning state by deciding in some situation, for example, that it is more convenient to abort a running activity than to wait for it to finish. The planning problem is again a classical planning problem, and we experimented using both fast downward and a planner that we have been developed internally for this purpose. At runtime, an automated planner is called through the Universal Planning Library, and it responds with a plan that is with the following activity to start, which of the following activity to start, to stop, or just to wait for it to finish. The executor is then responsible to actually tick the behavior tree associated with the activities that are running. The online planner is currently integrated in our behavior tree, and it controls the behavior of the robot in a specific condition. After an intensive quality assurance testing phase, it is in the process of being deployed on our fleet of more than 100 robots across our customers. We saw many impacts related to the introduction of a planner in our behavior tree. It simplifies the creation of behavior trees, as many conditions can be directly specified, and it's the role of the planner and the executor to take care of deciding which action should be executed in order to maintain the consistency. This relieves the behavior designer from the need to consider the possible interactions and sequences of events that can occur at runtime. In addition to this, the introduction of the planner also simplifies the trees themselves. Simpler trees also means a reduced probability of introducing bugs and a reduced maintenance cost. You can see in this slide the tree as was before introducing the planning technologies and after. Finally, as a side effect, the abstraction of the state and of the activities that was required to formalize the problem for the planner also led to a simpler definition of unit tests. Thank you for your attention.